Alright, this is the second little video over thermochemistry. We kind of ended with delta H in enthalpy on the first video. If you haven't watched it, you should go back and watch it before you look at this one. Enthalpy, be careful because we're going to talk about entropy today also, and so it almost looks exactly the same, so just be careful with it. So delta H, enthalpy, the amount of heat energy that is taken in or given off in a chemical reaction. By the way, you may hear my son practicing some oboe. Could be exciting. A little foghorn action. And so what this tells you is what we ended with last time. It's a great little review deal. Delta H is always negative if it's exothermic, because the system is losing energy. It's giving energy away, so it's a negative. Delta H is positive when it's endothermic, because that means endo means in. You're putting heat into the reaction, so the reaction is gaining energy, so a positive delta H. So exothermic negative, endothermic positive. It describes Hess's law in the next slide. This is Hess's law. Delta H equals products heat energy minus reactants heat energy to tell whether that reaction is endo or exothermic. We're not going to spend any time doing a Hess's law problem in this thing, but there it is. The overall enthalpy change is the sum of the enthalpy changes for the products minus the reactants in a chemical reaction. It's called Hess's law. So there are two things that contribute to spontaneity of reaction, whether a reaction occurs without any kind of outside additional outside force. And so these are the two things. The first one is the change in energy. That's your enthalpy that we just talked about. So this is our delta H. The second thing that contributes to the spontaneity of a reaction is the disorder or randomness of the particles in the system. This is described by a delta S, entropy, and usually we're looking at the states of matter here. So what state of matter has the most most randomness? Solid, liquid, or gas? It would be gas, because those particles have the most ability to move. So we'll see entropy here in the next couple slides as well. The great majority of reactions are releasing heat, are exothermic reactions. So in ectothermic, products have more or less energy than the reactants. The products have less energy, so energy is given off, and so we get that negative delta H. Most reactions are exothermic, are going to release heat as they go. The sun's going through a chemical reaction, it's releasing a ton of heat. Our bodies are going through chemical reactions, and they get hotter as more and more reaction is taking place. And so the great majority of reactions are exothermic, and you've seen that in class also. So things have a tendency to want negative delta H's, and they tend to spontaneously want more disorder, more randomness. And so this is the second piece of it. We have delta H, delta S, there's entropy. Be careful with the words because they look similar. The degree of randomness or disorder. If delta S is positive, we have increased disorder. If delta S is negative, then there's a decrease in disorder. What is the tendency for us in life? We want to be low energy. And if this quarantine deal hasn't been a sign of us wanting low energy, I don't know what does. A lot of us are sleeping till 2 o'clock in the afternoon, right? We want to be low energy. We want to lay on the couch and watch Netflix. Good. Here's the other thing. What else? The other factor that contributes to spontaneity is entropy, disorder. Particles are just like us. They want to be low energy, and they want to have high disorder, high randomness, right? What do we want to do? We want to go outside and go to a park. Why? Some of it's just to spite the authorities, right? There's all these protests going around because people are going, you can't tell me that I have to stay in my house, right? People seek this disorder, and particles do the same way. They seek randomness and disorder. And I always have somebody's like, I don't seek disorder. I seek order all the time. And I'm like, well, look at your room at home, right? Is your room naturally moving towards more order? Like if you're not paying attention, does your room get cleaner and cleaner, or does your room get messier and messier in The answer is your room gets messier. Even if you're super anal about where everything goes, you have to be super anal about it, or things will get out of place. And it's because all those things in your room have one place where they belong and an infinite number of places they don't belong. Nature is the same way, right? Where delta S, the positive, the increase in disorder, is the favored reaction, or the favored tendency. And less disorder is the non-favored tendency. And so it gives us that, think about solid, liquid, gas. Which change of state has the highest delta S value? The gas does. And so lots of times we look at reactions, and we look at the reactants versus the products, and we go, if products have more gas particles, they have more disorder. Good? If you're moving towards solids, you would be moving towards less disorder. Good? And the tendency is to move towards disorder. You lay an ice cube out on the table, what happens to that ice cube over a few days? It begins to evaporate, well, liquefy and then evaporate, right? It's moving towards that gas state. When we combine those two things, the enthalpy and the entropy, we combine it in this Gibbs free energy equation. Not like Barry Gibbs. You can tell by the way I move, I walk, a woman's way. Not the Gibbs brothers, or the Staying Alive brothers. This is Gibbs free energy. This isn't the Bee Gees Gibbs. But Gibbs free energy will tell you that if that delta G is negative, then a reaction is going to occur spontaneously. If that delta G is positive, then that reaction is non-spontaneous. Good. And so what two signs here would make this always negative? If delta H is negative, it's exothermic, and delta S is positive, more disorder, then that is always going to be spontaneous because of that minus T delta S there. Good? And so those two signs are the favored for making reactions spontaneous. We're going to do one little calculation here on the next slide. But negative delta G, spontaneous reaction, positive delta G, non-spontaneous reaction. That's good for us. And you can go through and look at all the different signs. If delta H was positive here and delta S was positive, this is only going to be spontaneous if we can make this factor really big. Good? And so we'd have to have a high temperature to make that negative enough to overwhelm that endothermic reaction and still make it spontaneous. So you can look at those signs and figure out what makes a reaction spontaneous, what makes a reaction non-spontaneous. And so they give us one here, and we'll work through this one. This one says, for the reaction of ammonium chloride decomposing into ammonia and hydrochloric acid at 298 Kelvin, that will be important. The delta H is this many kilojoules per mole, and the delta S is this many joules per mole. Be real careful with that unit. Delta H's and delta G's are in kilojoules, and delta S's are delivered in joules. So when we combine them all together, we're going to have to convert this joules to kilojoules in Gibbs free energy. This says calculate the delta G and tell whether the reaction can proceed in the forward direction. Good. It's asking us, is this thing spontaneous? Here's another thing to notice just for fun. Can we tell just from the reaction whether delta S is positive or negative? Is that reaction moving towards more or less spontaneous, or more or less disorder? Sorry, we're going from a solid thing to two gaseous things, which means our delta S should be positive. So that shouldn't surprise us that that's a positive 285. Good. Is this reaction endo or exothermic? The delta H is positive, so this reaction is endothermic. And so those factors are kind of butting up against each other, and we'll have to tell through this delta G whether they're spontaneous or not. So here we go. Delta G equals delta H minus T delta S they've given us a delta H here. Delta H is 176 kilojoules per mole. And we are going to subtract from that. T is the temperature in Kelvin. Why is it in Kelvin? Because look, that delta S unit's in Kelvin, so we got to have this in Kelvin. 298 Kelvin, that's room temperature, times our delta S. Now because this is in kilojoules, the delta S also has to be in kilojoules. And at this point, we should be able to convert that in our heads. That's 0.285 kilojoules per mole times Kelvin. And we can plug all this in and figure out what our delta G is as a result. I got to plug it in also, so bear with me. Be careful of your negative sign there. So we've got 298 times 0.285 gives me 84. When you plug this in, 84.93 for that piece of it. So we're going to have 176 minus the 84 point whatever, and we get that delta G is roughly 91.1. This is kilojoules per mole. See the Kelvin sign cancel out of there? So it's kilojoules per mole for the delta G. That's a positive. If it makes you feel better to see that positive, you can put that positive in there. Is this going to be spontaneous or non-spontaneous? This reaction is non-spontaneous because that positive delta G sign there means the endothermic overwhelms the increase in disorder, and so this reaction won't occur unless we apply some kind of outside force. I think I'm going to chop it there. We're 11 and a half minutes in. I'm going to do one, I don't know, 8 or 10 minute video on the collision theory next, and we'll talk a little bit about activation energy. So you can stick around for the next one if you want. See you soon.